talk about economies of scale, Costco versus convenience stores. If you want to purchase one single item, will you go to Costco or a convenience store? How about purchasing your needed products for the entire months in bulk for each? Will you go to Costco or convenience store? So the same thing happens with businesses. Actually, they need to make decisions about their quantity of purchase. So usually what happens is that convenience store numbers are huge. They are close by to the customers. It's easy for customers to walk to these stores or drive very short time. But usually Costco stores are large warehouses. There are limitations in the land, and also, the number of Costco stores are less compared to convenience stores. So usually customers take more time to drive and get to a Costco warehouse. So again, depending on your purchase quantity, you might decide which one works best for you. So let's assume there is a manager for a business placing order on different products. There are three main category of costs that happen. We talked about this in the previous lecture as well. Ordering cost, holding cost, and material cost. So ordering cost is fixed. It doesn't matter if we are ordering uh, one single unit of product or ordering 10,000s of units of product in one single order, the same cost will happen. Usually, ordering cost involved in administration paperwork. Doesn't matter if you're ordering one or 1,000, still you're going to pay that. So the manager wants to actually figure out what is the best decision. Should they order frequently in small lots? In this case, there is high ordering cost, meaning that you have to place several orders during a period of time. When you're placing order quantities, you have to do it over and over and over again. But holding cost is low because less amount of inventory, less holding cost. On the other hand, ordering infrequently in large lots, it means that the number of order placements are lower, so ordering cost is lower, but holding cost is high. The quantity you are keeping in a place, in a warehouse, in a distribution center, in a retail store is high. So you will have more holding cost. So depending on the business strategy, they might decide with any of these. For example, Amazon is more responsive, meaning that they want a large amount of inventories to be available, no empty shelves, no out of stocks for the customers, and therefore they consolidate orders in large bulks in terms of shipments, and therefore achieve economies of scale in their transportation, in their inventory, and lower the associated cost significantly. Let's take a look at the components of holding cost as well as ordering cost. So, what are the components? What are the factors that affect holding cost? First of all, cost of capital. It means that the money you spend to buy the inventory is sitting in a warehouse. If you cannot sell that, you're gonna lose that money. So you cannot use that capital over and over again. It's sitting there just as an inventory. Handling cost. So receiving and storing cost is regarding handling cost. So there are equipments in warehouses to move inventory around, inventory management systems, IT systems, and all that are related to handling cost. And also another cost is when we are working with trendy products, high-tech products, grocery products. So these can go to waste easily. They have limited lifetime. We have to sell this inventory on time. Otherwise, we are losing the money. We have to usually get rid of this inventory if it is not being sold on time. And also occupancy. So the space we are using to keep that inventory, the energy related to the space, and any other operational costs related to this space, and also other kind of costs such as theft, security, damages, taxes, and insurance of this inventory also includes in holding cost. And then components of ordering cost. When we are placing an order, we have the buyer time, first of all. The buyer time is related to a person we are hiring to sit there and do the work. If they are not fully utilized in terms of their time, as we are increasing their workload to some extent, they can handle it. But if we increase after a threshold, we have to hire another person to help them. So depending on the level of utilization, basically of a person, their salary matters. Basically, the time they spend on the work matters. We will we will see some costs associated to that. Transportation cost is part of ordering cost. So if we are using one truck to move and ship all those products to our warehouse, then if you're using only half of that truck capacity, basically, as long as we add to the truck, add products to the truck until we get to the full truckload, we are not really seeing much of a difference. But after the truck is full, adding another truck increases obviously the cost. So again, it is a decision. Do we need 5 trucks, 10 trucks, 10 trucks and a half? So where is that optimum um, cut off, right? So we want to decide about it. And receiving and administration costs, all the paperwork related, all the IT system related, everything that's going to help us actually placing the orders and receiving the order and then checking the quality of received products and making sure that everything was actually shipped and there is no damages and stuff. So those are also part of ordering cost. So considering all these different components of different kind of costs, we want to decide what is the best quantity to order so that we can minimize all these costs at the same time. So basically, we want to minimize total cost of inventory, which is summation of annual material cost, annual ordering cost, and annual holding cost. I will show you actually next some formulas how we can actually do the calculation and figure out the optimum level of ordering. But we do have some assumptions to simplify the problem here. A single product is being purchased or manufactured. Demand is steady over time. No shortages allowed, meaning that there is not a case we have lost sales. And also replenishment lead time is fixed and usually considered zero, meaning that when we are placing an order, it will be immediately available as inventory in the system. So considering that, we can actually calculate the minimum total cost. So let's look at this graph. In this graph, we have the red curve, which is ordering cost. So if we are ordered in small quantity, lot size, ordering cost is high because we have to place orders over and over again during a year. If we are ordered in larger quantities, the number of orders will be less, and therefore ordering costs will be less. The blue line is holding cost. If we have low amount of inventory to hold in a place, holding cost will be lower. If we have large quantity to keep as inventory, holding cost will increase. Material cost is to some extent constant. If we are ordering larger lots, usually we can get some sort of discount, so a little bit less when order quantity is high. Then we gotta sum up all the 3 costs and draw the total cost curve. At the beginning, if we are ordering in low amount, the total cost is high because of the ordering cost is high. As we move into larger order quantities, this total cost drops. And then at some point, again, it increases. The reason is that holding cost increases as well. So there is a point where total cost is minimized, the lowest total cost. That shows us the optimum order quantity, Q star. So here is where we want to figure out and the quantity that we will place the order. That's going to help us to minimize all costs at once, which is perfect for the system. So here's the formula we have for EOQ. I don't want to go into details of the mathematics behind it, where this formula is coming from. Maybe you can think about it and let me know. Uh, can you calculate this? Can you figure out where this formula is coming from? And if you have any questions, feel free to reach out to me. So, in order to calculate this Q star, which is the economic order quantity, EOQ, which minimizes all the costs, we're going to use D, the demand, and S, the fixed ordering cost, H is the holding cost as a fraction of unit cost, and C is the material cost. We can also calculate the optimum order frequency. So let's say that in 1 year, how many times I should place an order? 10 times, 20 times, 100 times. What is the best action to take that minimizes the entire cost? So Ed star will tell us that. Dividing demand by Q star, the EOQ, will give us N star, the optimum number of times that we can place the order. Again, this is the simplified version how things work. In real world, businesses have more assumptions, realistic assumptions, and therefore they have to manipulate these formulas and make sure that they account for those complexities. As we have more assumptions, we change the mathematical models, and also there are new techniques in machine learning, artificial intelligence that can help us solve these complex problems more basically faster and make sure that we have a good output, a good decision that can help us lower all the costs involved in inventory. So let's take a look at an example here. Let's say that Best Buy is selling computers and they want to actually place order and have inventories in the store. We do have some given information. So their annual demand, their monthly demand is 1,000 units. So the annual demand will be multiplied by 12,000 units. Order cost per lot is $4,000 and unit cost per computer is $500. And holding cost is a fraction, which is 0.2 based on the input data of this example. So the store manager at Best Buy wants to figure out how many units of computer they should buy each time and keep in the inventory to make sure that they can fulfill the demand on time. So we can use Q star, calculate Q star, EOQ, to give the answer. So we know the demand, annual demand, we know the ordering cost, we know the H, which is the fraction of holding cost, and also material cost. So the manager should place 980 units at a time to minimize all the costs involved in their supply chain. And they can calculate cycle inventory, which is the Q divided by 2, which is 490 units. The manager has another question asking that, hey, what will be the optimum number of times that I have to basically place the order, or what is the annual order get holding cost in that case? What would be the average flow time for all the units of product to be sold? So we can actually do the calculations as well. In terms of N star, number of orders every year, we can divide a D by Q star and it is 12.24. So it is not an integer, obviously. We cannot place 12 order and what? It's not even one single full order. So then we have to actually round it up or down. 12 or 13 seems to be reasonable in terms of minimizing the cost. And also we can calculate the ordering and holding cost with these formulas, and also average flow time, Q divided by 2D. We talked about this in the previous lecture. If you haven't watched it, please go first watch that and come back to this lecture. And so basically it is 0.49 months. The amount each computer spends in average in Best Buy store is this uh, much. So let's look at some insights based on our example. First of all, sometimes we calculate EOQ, the Q star, and we don't have to go exactly with that number. Obviously, that is the best possible option in minimizing all the costs, but sometimes it is okay to round things up or down. For example, in this the Best Buy example, Q star is 980 units. Uh, Maybe if we just round it up into 1,000 units, it is much more easier to handle in one full truckload, and the manufacturer doesn't have to, make adjustments for us, right? So instead of 980, we can order 10,000. It's not that much of a difference in terms of costs. Also, based on the formulas that we talked about, it shows that if demand increases by a factor of k, the optimum lot size increases by a factor of square root of k. So what does this mean? Actually, this is based on our formula. So demand is, if demand changes into d plus k, k is under square root. So it is square root of k that Q star increases. So there is not linear relationship between demand and order quantity. It is non-linear. If demand goes up, we are not exactly adding that number to our Q star. It is a square root of that number that should be considered adjusting Q star. And the same thing with the optimum ordering frequency with demand. There isn't a linear relationship. And also the lot size, in terms of lot size, so to reduce the optimum lot size by factor of k, the fixed ordering cost must be reduced by factor of k2. And where this is coming from is from our formula again. In order to get rid of square root, we have to make Q star to the power of 2, this entire thing to the power of 2, so that we can get rid of this square root. So Q star to the power of 2 then has a relationship with the ordering cost. Hopefully these are clear. If not, just let me know. I would be happy to provide more information. So let's take a look at an example. Maybe this helps better to understand what exactly happening here. So let us talk about the situation with Best Buy. So we are placing 1,000 units of computers. Let's say that manager would like to reduce the lot size to 200 units. So manager says that I don't have the money and the budget right now to place 1,000 computers, even though EOQ is telling me that's the best action to take. I don't have that budget. I just want to place 200 units of order at a time. So then what happens to all these costs? We can help them, right? We can do the calculations. So if instead of 1,000 units, the manager places an order to 200 units, then we can calculate annual inventory related cost, which is ordering cost and holding cost. It's going to be $250,000. In our previous example, when we helped them to do the calculation of Q star, and then based on Q star, the annual ordering and holding inventory cost was around $98,000. So if they reduce Q star from 1,000 to 200, they incur way larger cost, which is $250,000. So it is a large increase, obviously, but again, they have to figure out if this is something that works for them, right? Again, if the budget is limited and so on and so forth, then we have to work with it. But let's say that they have this desired lot size of 200 units, and let's say manager says, okay, I see that my inventory related costs are really high if I order only 200 units. Can you help me to do some more calculations? So for this lot size reduction to be optimum, let's say that I want 200 units to become optimum lot size ordering for me. What other costs should I reduce to get there? Help me figure out what should I reduce in terms of cost and so that this 200 units become optimum for my case. So the desired lot size is then 200 units. Annual demand is still 12,000 units. Unit cost per computer, every single computer costs 500 units to be purchased, and still holding cost is the fraction 0.2. So by knowing that, we can actually figure out the desired order cost. How much the order cost should be reduced so that 200 units make sense and become optimum, new optimum order size. We place the numbers in here and then do the calculations. I want you to recognize that S has relationship with Q star. So Q star to the power of 2 has relationship with S. And that's what we talked about in this box here, right? So if we want to actually reduce the order cost, we have to we have to work with order quantity to the power of 2 rather than order quantity itself, right? So that is how things are being affected. So if the manager wants to keep 200 units of order and make it optimum, they have to reduce their ordering cost into about $167. If you remember in the previous example, it was $4,000 of ordering cost. They have to reduce it significantly into just $167 in that case. Maybe they have a lot of administration costs they can cut. Maybe there are many people but not being utilized full time. So again, they have to go and figure out if they can do this change. So depending on the situation, we can work with numbers, we can work with these formulas and try to figure out what can be the best action to take. Some real-world applications of cycle inventory principles. Obviously, Toyota is one of pioneers trying to reduce cycle inventory. They manufacture based on demand, and they built this lean manufacturing system, not keeping that much of inventory and being able to um, lower the waste in the system. Walmart uses cross-docking for their transportation and aggregation of shipments to their warehouses. Cross-docking is a way that where we can actually ship things in full truckloads to a location, to a cross-dock, and then dispatch into smaller sizes to the last destinations. So usually we don't keep inventory in cross docks. It's just a way to where we can actually um, work with the shipments, making sure that we can use economies of scale with full truckloads and then get closer to the customer and then break it down in smaller shipments. And Amazon, obviously, Amazon is doing a lot of using a lot of new technologies to reduce their holding cost, as well as their transportation cost, since they are consolidating, orders into large shipments and reducing their transportation cost accordingly. So, in order to test what we talked about in this part of the lecture, I have 3 questions. Please pause this video, think about the questions, and then you will find the answers in the next slide. Question number 1, a retailer has annual demand of 5,000 units, fixed order cost of $200, and then cost of material is $50, holding fraction cost is 0.25. I want you to calculate Q star, the optimum lot size, order quantity, and also calculate total ordering and holding cost based on this information. Um, Question number 2, if demand doubles, so K is 2, what happens to Q star? And also what happens to N star? Do they have linear relationship or nonlinear relationship? Question 3 is a manager wants to halve the lot size. So K is 2 still, but divided by 2. But by what factor must fixed order cost S be reduced? So again, is there a linear relationship or not? You need to think about it. And why is this critical for lean operations? We talked about lean manufacturing, reducing the waste, lowering cycle inventory. So think about it, how this can be affecting lean operations. All right, please think about the answers and you can find them in the next slide.